So next we discuss the matrix representation of eigenvalue problems. Now a quantum mechanical problem can be formulated either in differential equation form or in matrix form. And in both form, the solution consists of finding the eigenvalues and eigenfunctions of the operator associated with the corresponding observable. So let's consider the eigenvalue equation of an operator A with an eigenvalue small a such that A acting on psi should give you small a psi, where small a is the eigenvalue of the operator A. Now we insert the unity operator between A and psi. That means A summation over n phi n psi is equal to a psi. If we multiply both sides by bra phi m, this will give us summation over n bra phi m a phi n psi is equal to a phi m psi. Now let's rearrange the terms. This can be written as summation over n. All these terms are given by the matrix element AMN, right? So this is matrix element AMN. Then what we have is phi n psi is equal to, now on the right hand side, let's make some trick. So this can be written as summation over n phi n psi delta n. Now this is same as this expression, right? Because of this delta function, out of many of these kind of terms, you will get only one non-vanishing term, and that is given by phi m psi. So this is same as the above one. Then why did we do that? This is just to make the left and right hand sides look similar. Now you can see that this phi and psi is identical on both sides. You have phi and psi. Okay. So this can be rewritten as summation over n AMN minus a delta mn into phi n psi is equal to 0. Okay. So AMN is the matrix element given by the product of these matrix. Okay. So this is the equation that we get. Now you can see that now we have considered a basis phi n for this expansion, right? Because we have written or we have introduced the unit operator in terms of a phi n basis. Now this basis is made of an infinite number of base kits. So this equation represents an infinite homogeneous system of equations for the coefficients phi n psi, right? So this system of equation can have a non-zero solution if its determinant vanishes. That means the determinant of AMN minus small a delta mn must be 0 in order to get a non-zero solution. Now to solve this, we need to truncate the basis phi n so that it contains only a finite number of terms. So let's truncate, let's assume that it contains a finite number of kets. Now in this case, this determinant equation reduces to an nth degree determinant. This will reduce us to an nth degree determinant. So in this case, we can write this determinant equation is something like a 1 1 minus a 1 2 a 1 3 etc. a 1 n. There will be n times a 2 1 a 2 2 minus a 2 3 etc. a 2 n a 3 1 a 3 2 a 3 2 minus a 3 n. Then it's like it will be having a n 1 a n 2 a n 3 etc. up to a n n minus a. Determinant must be 0. Okay. Now so this is known as a secular or characteristic equation. Secular equation or characteristic equation, and you are familiar with these kind of equations. You might have studied it in matrix algebra class. Okay, so the solution of this should yield n eigenvalues. So the solution of this equation will yield capital N eigenvalues. What are those eigenvalues? A1, A2, A3, etc. up to An. So if knowing these set of eigenvalues, we can determine the corresponding set of eigenvectors phi 1, phi 2, phi 3, etc. like this. So this is a normal matrix algebra that you do with eigenvalue equations or eigenvalue matrices. Okay, so once you know these eigenvalues, you can determine the corresponding eigenvectors. For each eigenvalue am of the operator A, we can obtain from the characteristic equation the n components. The n components, what are those components? Like a phi 1 psi, phi 2 psi, etc. up to phi n psi of corresponding eigenvector phi m. Right? So for each of these eigenvalues with a corresponding eigenvector phi m, n components can be obtained from the above characteristic equation. Now if a number of different eigenvectors have same eigenvalues, then this eigenvalue is said to be degenerate. Now the order of degeneracy is determined by the number of linearly independent eigenvectors that have same eigenvalue. Now, one important aspects of this is that the eigenvalues of the matrix eigenvalue problem will be independent of the basis which you use. So in the case where the set of eigenvectors, if the set of eigenvectors phi n of the operator A is complete and orthonormal. So if this set of eigenvectors is complete and orthonormal, then this set can be used as a basis. This can be used as a basis. So it form a basis for the expansion. So in this basis, the matrix representing the operator A must be diagonal. So let's see that. So we have seen that the matrix element AMN is basically phi M A phi n, right? Now, if phi n is an eigenvector of the operator A, this can be written as small a into phi m phi n, because A acting on phi n will give you this eigenvalue times the same eigenvector. So this is A delta mn if it forms an orthonormal set of bases A delta mn. So that means you can write this vector A in these bases as A1 0 0 etc 0 A2 0 etc 0 0 A3 etc. So like this. So you get a complete diagonal matrix if you expand it in this basis phi n in this basis. Okay. Now the use of Hermitian operators gives us some advantage because the eigenvalues of Hermitian matrices are eigenvalues of Hermitian matrices are real and the eigenfunctions or eigenvectors or eigenvectors form an orthonormal basis. So when we use Hermitian matrices, the eigenvectors form an orthonormal set of bases. That means, like what we have seen just before, any operator will be a diagonal operator with the diagonal matrix with the diagonal elements being the eigenvalues. So it's a straightforward way of obtaining the eigenvalues of operators. Okay. So next we consider the Schrodinger equation in matrix form. So let's consider the time dependent Schrodinger equation in differential operator form. So this is given by I h cross dou by dou t of psi of rt, this is equal to the Hamiltonian psi of rt. Okay. Now let's consider a basis phi n, a set of basis phi n. Then in this basis, the psi of rt can be written as psi of rt can be written as summation over n an of t phi n of r, where an of t is the expansion coefficient. We have seen it many times. So this equation can be written as, the Schrodinger equation can be written as IH cross d by dt summation over n an of t phi n of r is equal to the Hermitian operator summation over n, then an of t phi n of r. Now let's multiply with bra phi m of r both sides. Then this will give us IH cross d by dt summation over n an of t phi m phi n, and on right hand side what we have is summation over n. Since h is an operator, the Hermitian operator, then what have to you have to multiply from left side from phi m h phi n, and then we have an of t n of t. So this is given by a delta function delta m1, and this is given by the matrix element HMN. So we can write IH cross d by dt of, see what we have is a summation and an of t then delta mn. Then out of these many possible terms, the only surviving term will be a m of t when your m and n are equal. So this will be a m of t equal to summation over n h m n an of t. So this is the matrix form of Schrodinger equation.